The first talk is by Daniel Sauter on why antivirus software fails. And yeah, we're looking forward to it.
Okay, so thank you for coming to my talk, which is about why antivirus software fails, and of course has something to do with antivirus evasion. First, who am I? I'm IT security consultant. I'm doing pen testing since a little more than 2 years. This talk is based on some private research, and before starting in IT security, I have some experience with Windows, Linux, and network admin, and also a little as web developer and so on. So I have 2 parts. In the first part, I will explain some basics of antivirus evasion, which has mostly 3 steps, as I said. We will see more about this soon. In the second part, I will go a little bit deeper in how antivirus software is working anyway. So we will have a little more about code emulation there, about antivirus evasion using Windows API calls, and what's going on with 64-bit. So I started writing my own antivirus evasion tools about 2 years ago. Yes, when I started as a pen tester, of course. The techniques I used there showed me very much how antivirus software is working. Last summer, I started testing this a little more systematic, using more AV evasion techniques and with more engines. And I also did some research about code emulation. So my motivation of this, of course, was at first having my own antivirus evasion tool, and doing more and more about this, I started to realize where the limitations of antivirus software is. So first, some words about my testing environment. The focus is Windows, of course. In my testing environment, I used most Windows XP, but also Windows 7 and Windows 8. I used Backtrack as my attacking machine. I used Metasploit for generating the payloads, because the payloads are well known by the antivirus software, and if you can hide this, you have success. I used MinGW as a compiler, NASM, OllyDebug, and Visual Studio, and also VirtualBox. I did some testing in a virtual environment, but also on physical machines. So nothing special here, so, just some machines I used there. Here's the folder with my proof of concept stuff. It's not all, it's a older screenshot, so yeah. So, and here I got a shell, yeah. I think everyone knows how it looks when a shell pops up. So I got no live demonstration here about this. I think most people know that antivirus evasion is working generally. So what are the basic steps for doing antivirus evasion? In the test scenario, of course, Windows, MSF payload. I won't explain every detail because I already wrote an article about this, which is in the link section of the slides, and you can download this if you like. You can download all the examples I'm showing here from GitHub. I had to think a little about this, if I'm doing this or not, and I decided to give my examples away because I have some more of them, which I don't show here, so it's okay. So, as a first step, we need to have an own shellcode binder. So, why is that important? We need this to evade the pattern-based virus recognition, because, for example, the Metasploit loader is recognized even if there is no payload in it. So even if you have an exe file which has no payload, any product will say this is a virus, although it isn't doing anything. So we need to do that on our own, and this is how it works. Here is the file name from the repository. It's pretty simple. You have your shellcode, and this is more or less a simple function pointer, so nothing really strange here. Then we need to encode or encrypt the shellcode as a second step to evade the pattern recognition. As you can see here, this is a simple example for this. You can see the whole code, if you like, from the repository too. My encoding is pretty simple. I'm just doing a kind of hex to ASCII encoding here, and then I'm decoding it. And after decoding, the shellcode is being executed with the binder I showed before. So if you want to know more about the encoding, you can read the article, but it's pretty easy. Then, as a third step, we need to evade the sandbox or the code simulation. Why do we need that? Because the file is still recognized as malicious, at least by most products, and because of the sandboxes, or better, the code emulation. So why are the products doing code emulation? Because that's simple. A virus can be encoded in any way, as I'm doing it. And if a code emulator is executing the exe file, the virus has to be in the memory, and then you can do pattern recognition. And the file will be recognized. But you can stop this. So what to do now? Yeah, something to stop emulation. And in my example, I'm just opening a file, as we can see here. So nothing very special here. I just open a file. Later, I found out that that the file doesn't even to exist. So that doesn't matter, because the code emulator is simply stopping it. It's saying, oh, okay, something really strange here. We open a file. That's I can't do this, and I stop here. There's no pattern matching, so the file is okay, and the user can execute the file. So pretty simple. So that was it for the first part. I used these 3 steps all over again. The first 2 steps are the most important, And for the third step, I tried to find more exploitation techniques. So, after having my first programs to do antivirus evasion, I realized that the antivirus programs are seem to be limited in code and API emulation. So, yeah, I started developing more techniques to find more out about the emulation part. So, let's have a look. First, let me say a little more about code emulation. I took one example here. This is libemu. Anyone works with this here? libemu? Okay. Obviously not. It's a tool for emulating shellcode. It is executing the shellcode instructions, reading binary code, doing register emulation, have some basic FPU emulation, and you can write your own Windows hooks. So it's pretty simple. If you want to learn more about code emulation, this is definitely worth a look. Generally, code emulation works in a big loop. So one moment. So one command is one command after another is executed there in the emulator. If you want to know more about this, you can read the excellent book here by Peter Shaw, The Art of Computerized Research and Defense, which will explain more about this, but I think the concept here is pretty obvious. So how does that look in reality? This is from the paper Software, a critical analysis of Software's antivirus. And this paper is from the end of 2011. And it hasn't become better since this. So here you can see a few things. The emulation is poor representing and only executed for around 500 cycles. Here is sufficient to subvert emulation and so on. And of course, the emulation is pretty limited when you have only 500 cycles. This is pretty clear, and of course you have to implement it the right way. So why only a few hundred or a few thousand cycles? This is just because the user wants to use the program. He doesn't want to wait for 30 seconds or something. So the emulator is just for a very short time. So we have seen that the emulation has some limiteds, and here a little more interesting part can start. And I will show you some proof of concept codes. So first, I did some basic testing just to have a line, or yeah, to look how good antivirus detection works. So with ICAR, MSF payload generated exe file, Shikata Ganai with 5 rounds, and the well-known syringe tool, which surprised me a little after compiling it. Only one product recognizes this as malicious. So if ever you want some really simple antivirus evasion, you can go on and use syringe. You can just Google for it. It's pretty easy to find. So the first one is the examples I already showed. It's just the shellcode binder called no encryption because there's nothing encrypted, or anyway, it's really just the shellcode binder. And it is 4 of 9 products failed to recognize the file as malicious. So, and it is successful in at least one product that officially has code emulation. So, guess which one that was. And I have one more doing the encoding, but no sandbox evasion. And here are 5 of 9 are failed to recognize it. So then I started doing some research about standard calls and Windows API calls. As first again, the file open example, where 9 of 9 failed to recognize it. So this is pretty good. And also pretty simple. This is an old technique. I discovered it by myself, but then I realized that more smart people found this one too. So this is really old and it's working. Another example is you can use some math calls here, just random stuff. This one works because the engines are only doing a few hundred or a few thousand CPU cycles, and then break it up and say, okay, go on. Later, I saw in another example that it would be enough just to do a for loop, which is counting to 10 million or something like that. This would be also enough. And here, also 9 of 9 products failed. Here is something else. This example needs some help from the user. I have a getch here. So when the user is hitting return, the payload is being decoded and then executed. And this one works in 8 from 9 engines I've tested. So a long time ago, there were these examples where only a message box is popping up. And when the user is saying, okay, it is going on, this doesn't work anymore because the antivirus software seems to recognize this and just goes over this part. But not here. And you can also use scanf, which is pretty much the same. Then I tried more with Windows API calls. And here I simply opened an event log, the application event log. Just opening it is enough. You don't have to do something with it. And again, the 3 steps here, decode and then exec. So nothing really special. Yeah, here you can see that most engines really can't emulate the Windows API calls, and they don't jump over it for looking what is happening behind this part. So this might be a good idea. So this example is from the last year's talk by Attila Marosi, Easy Ways to Bypass Antivirus Systems. This one, I think it is pretty nice. It is just looking what is the name of its own file, of the exe file. And if this is not working, the payload isn't being executed. So pretty straightforward, and I really like this example. Yeah, very simple. And here too, 9 of 9 products failed to recognize this file as malicious. So here I am opening a listening socket and doing nothing else basically. I just opened the socket. This is the sandbox evasion part again, and that was it. Some times ago, this works with connect sockets too, but they improved it a little, not so much, because this was one of the very first examples for doing sandbox evasion. So now, what is it with 64-bit? The results here were a little surprising for me because, yeah, 64-bit is really not that new. And most enterprise-level products really seem to have a problem here. For example, this one is really pretty straightforward. There's no encryption in it, there's no sandbox evasion in it, and only 2 products recognized this one. And one was Avast free, and the other one was Commodore free. And many enterprise products I've tested failed with this one. So I was really wondering about that, because this is simple pattern recognition, and it's well known for years. So, Then I wrote my own shellcode binder for 46-bit. I can tell you this is enough. 9 of 9 products failed. Of my tested products failed. So the big difference to 32-bit is that you need to make the memory section with the shellcode writable and executable first, and you can do this using the virtual protect function. Yeah, this one was new to me, but yeah, as you can see, pretty straightforward too, and nothing more has to be done here to accomplish the goal of antivirus evasion. So then I did some more research about MMX. For this, I took an example from the Security Tube Linux Assembly Expert certification. So I can show the example here. And it is simply using the MMX registers to encode the malicious payload. And only 6 of 9 products failed here. This was surprising to me too. If you compare it to the 64-bit registers, yeah, to me that was a little surprise. So I didn't do more research about MMX or FPU. I started it, but it seemed not so necessary to do more research here. So this was pretty fast. So I'm already at the conclusion. The antivirus software has some limits in signature recognition, which can be bypassed easily in API call emulation and in processor emulation. And even if features are implemented, this doesn't mean that those features are working. And yeah, it's more or less all a question of the effort an attacker puts in his attack. So the effort in antivirus software can be considered as low. So these techniques are well known. You can Google them. If you know a little about programming and IT security, this is pretty simple. And for example, Black Hole and so on, the exploit kits are doing this by standard. So there's nothing special about this. Now I show some more of my detailed scanning results. Here's the basic section, so nothing that interested. This is a syringe example. As you can see, red means that the antivirus software fails. I did some testing too by only generating the payload without a shellcode binder. You can see this here. Oh, there's an error here. Okay. I think I won't explain each sample here. This would just cost too much time. But what is really interesting is that the big red blocks here and here, they mean that the code emulation failed or that it isn't implemented. I think at least 2 of the products here say they have code emulation. If not 3, I'm not really sure. So as I said before, the message box example did some time before. Of course, it is working on the products that don't have code emulation. Yeah. Okay. So I did some more testing, but yeah, I just showed the most important examples. So more. As you can see here, we have 2 samples that work everywhere too. Here it's the string C, and the this one is just incrementing in a for loop. So this is another example that is interesting, but it's more or less like the math example. Yeah, and this one was the more surprising part. The MMX decode example worked only in 1 product as a sandbox evasion technique. So I thought this would be more successful, but yeah, that's it. So, and here are the detailed results for 64-bit. I even wrote some more POCs, but that was not necessary. I wrote them before I started all the testing, so that was basically my own fault. And what I found interesting is that, for example, Bitdefender, but this might also be a false positive, recognized the payload, but not the exe file as malicious. I don't know why, but I really think it's a false positive here. And no sandbox evasion is necessary when doing 64-bit, which might mean that there's no code emulation in use here. So for me, this is pretty obvious, but I don't know. Maybe it's not being used or it's broken. So, and what can you do now as an administrator or as an IT security guy? I think the best would be whitelisting. Of course, this is not that easy and it has to work correct. You need to do more manual analysis and distribute the new signatures. Maybe this would help, and of course the usual. You can't do so much against an individual attack. So you have to look what to do afterwards. You have to be aware of the danger. So you should do log file analysis, have a SIEM, and of course training your users, which is the most important part here. This is too important for private users. They can't just say, oh, I have antivirus, now I can do whatever I want. This, of course, is a little problem. So, some links. Yeah, we don't have to go into this deeper. And yeah, that was basically it. Thank you.
Thanks. So we've got more time for questions. Any questions from the audience? Have you seen other publications concerning the 64-bit fail?
No,
because this is really frightening.
Yes.
Looks like none of the antivirus research is going into this direction. So, or are these 64-bit emulators so complex, or what do you think the reason is?
I don't think they are more complex than 32-bit code emulation, because you just have to have other registers.
Yeah.
So I don't know, and I mean 64-bit malware is also nothing new.
Yeah.
So I'm really wondering about this. Yeah.
Yeah. That's the question.
So I might have missed it, but you mentioned how people used to, you mentioned the general technique of waiting for user input before continuing on and executing. And you said that people used to just pop up a dialog box that said okay, and they would wait until they hit it. And you said that that's combated now, but I didn't see source code for that, and I don't think that that was in your statistics, was it? So did you actually test that against the 9, and was it that they all caught it, and so you just didn't show it?
I had it in my
Okay,
slides.
all right, then I missed it.
Should I show you?
No, that's fine.
Okay,
I'll
okay.
look at it later. Thanks.
I've tested this. Yeah.
Further questions?
Okay.
No more questions. Then thanks a lot.
Yeah,
We are
thank you.
continuing at 10 to 5.